Hey guys, welcome back everyone. This is me, Rooney Lin, and today I'm going to do another brilliant.org educational video created as I mentioned to you previously. This time, however, I'm going to show you that very fascinating topic from science category. See the science in the world around you. And more interestingly, I'm going to do the chapter from here, kurzgesagt, beyond the nutshell. Sorry, actually it pronounces kurzgesagt. Kurzgesagt. That's the word in German, like explain for science. I'm going to do that exercise. Very unique chapter here, I assume. So I'm going to click it. Yes, the objective is to dive into the science behind your favorite kurzgesagt videos. So collaboration with this official YouTube channel like related to science. From this level 2 disasters, I'm going to, of course, do about a topic called climate change exercise that I want to briefly describe how you read the exercise lessons from every particular topic. So I'll click start here to begin. You wait for a moment to get this loading. Right, here we go. The lesson begins. Climate change. Lately, it seems the news is always full of natural disasters, droughts, floods, wildfires, and hurricanes, whose severity is at least partially attributed to climate change caused by, of course, human activity. So these flood and drought contrasting disaster showing on display here. The average global temperature has risen by about 1 degree Celsius since pre-industrial times, and you may have heard that we need to keep this rise below 2 degrees Celsius to avoid further worse effects. Now, let's investigate what's causing temperatures to rise and then examine how likely we are to avert this climate disaster. Right, I'll click continue to display the next screen. Here, if I scroll down, to explain why Earth's temperature has risen in recent decades, we need to understand what determines its temperature in the first place as well. Now, if an object's temperature isn't changing, what should be true about the energy flowing into and out of it? So, assuming temperature is constant, unchanged, so only one of them is true. Of course, flows in and out should be equal, this option. Let's click on it. That's right. If an object's temperature is constant, that means its net energy flow. So review here for definition. Being more precise, when we say energy flow, we mean energy per unit time, also known as power, which is typically measured in units called watts. It is equals 0. The energy flowing in is equal to the energy flowing out, kind of energy balance in the first place. Excluding the last century or so, Earth's surface temperature has stayed the same for thousands of years. There were variations day to day and place to place, but averaging across the whole Earth, the temperature was basically constant. Continue to the next screen. This means the energy flows into and out of the planet were balanced. Let's identify and quantify them. So you see this diagram that I just explained? Where does the majority of energy flowing to the Earth's surface come from? Of course, can't be the Earth's molten core or rotation. It must be the sun. That's right. You got it. The Earth's surface is warm thanks to a constant flow of energy from the sun. Energy, what we know as the sunlight. Sunlight's average energy flow per unit area. Its intensity on the Earth's surface is given by I. The total energy flow in is the product of this intensity and the area A. It's incident on this formula. F in equals A times I. So total energy flow per unit area equals area A times surface intensity I. Basic as that. Continue to the next. For Earth's temperature to remain constant, energy flowing out from Earth's surface must balance absorb sunlight. Where does this energy go? Let's see. It cannot be flow into the ocean or absorbed by plants. Emitted into space should be out of energy like this. That's right. Just like the sun, Earth is radiating energy out into space. You just can't see it with the naked eye. Because energy is invisible, so it's playing like not visible by every human being. In this diagram, like every energy out of the planet is released as energy emission into outer space, like in multiple directions, showing these arrows. In fact, all objects are constantly emitting energy out towards their surroundings in form of called radiation. The amount and type of radiation changes with temperature. Earth emits invisible infrared radiation. Metal in a forge glows red, and the sun shines bright with visible light. Continue to the next one. I need to scroll down. Wait, I need to read this first. The radiative energy flow out from an object depends on its temperature, measured in an absolute scale like Kelvin. This says like temperature scale has 0 coincide with atoms having no vibrational energy, lowest the record temperature roughly minus 273.15 degrees Celsius. You see that Kelvin is the most common absolute scale. Convert from Celsius to Kelvin, simply adding 273.15. Room temperature is around 295 kelvins, and so on, and its surface area. More precisely, this flow is proportional to temperature to the fourth power. This means Earth emitted radiation in the form of a constant C, its surface area A, and its temperature to the fourth power. So, energy flow out equals constant times surface area times temperature to the power of 4. The strong temperature dependence is illustrated in this plot, which shows the energy flow from a 1 meter square patch of Earth. Wait, constant. Actually, this constant is based on object emission temperature in this area, the Stephen-Boltzmann constant, named after Joseph Stephen and Ludwig Boltzmann, two physicists who studied thermal radiation. This Stephen-Boltzmann constant value approximately 5.67 times 10 to the power minus 8 watts per meter squared per Kelvin to the fourth power. Just basic definition overview. So if I scroll it down, yes, energy flow from 1 meter square patch of Earth, so like around 150 kelvin, this 29 watts, increase exponentially over temperature change. Emitted radiation will also increase rapidly as we shift temperature far to the right as increasing. Let's continue anyway. How much does emitted radiation increase when temperature increases from 255 to 280 Kelvin? Let's assume it. 280K. Immediate radiation. Immediate radiation. If I could assume it, wait, there's no such given. I say about by about 10%. Let's check. So about 25%. No, by about 50%. I just simply don't know why that's the correct answer, but let's click why for its reasoning. 255 Kelvin, about 240 watts per meter square. Oh yeah, I think I should use calculator, but unfortunately I don't have time for that. Compared to about 350 watts per square meter at 280 Kelvin. Probably using the calculator should be much better, but I generally don't prefer that. So 250 divided by 240, approximately 1.46, correspond to 46% increase. Kind of mathematical calculations that we have to consider in the first place. Let's click continue anyway. Increasing absolute temperature only about 10% can increase emitted radiation by significantly more. The energy flow out of Earth is strongly dependent on its temperature, but we'll use this relationship to figure out how hot the Earth should be. Right, just brief summary how temperature increase affect radiation emission in terms of proportionality. Continue. Earth's temperature will be constant when the two energy flows are equal. This happens at the equilibrium temperature called TEQ. As this balance absorbs sunlight equal emitted infrared, F int equals F out, A times I equals C times A times T equilibrium power 4. As a first step to solving Earth's equilibrium temperature TEQ, isolate that TEQ term. So we'll cancel A from both sides. It should be I divided by C. Done, and check it. Yup, that's correct. Why for reasoning? Since both flow depends on Earth's area A, divide from both sides. So I equals constant times TEQ power 4. As I mentioned, area A will be cancelled. Then isolate TEQ term, divide by C, so use the following answer that you just expected. Continue for the next one. We can then solve for TEQ by taking the fourth root of both sides to get an equation for Earth's equilibrium temperature. TEQ equals I divided by C, which is square rooted power 4. This equation provides the simplest model we could use to predict TEQ, since it only depends on sunlight intensity. Overall, it basically used the plot from before in reverse. For some energy flow per area, it gives the temperature corresponding to the magnitude of radiated flow. Now let's see and observe how well it does. So I'll click continue here. So yes, the effective average intensity I of sunlight reaching Earth. The intensity when you consider that Earth is a sphere and sunlight only comes from one direction is roughly 340 watts per square meter. Now find the equilibrium temperature corresponds to I equals 340 watt per meter square. I need to, yes, just drag the y-axis and identify equilibrium temperature. So I need increase to 340. So like this, approximately 238 kelvins. So check. That's correct. So why for reasoning? Adjusting solar intensity to the desired I equal 240 watts per square meter, we can simply see from the plot that corresponds to equilibrium temperature about 278 kelvins. Yes, basically simple problem to solve. Continue. The intensity of sunlight on Earth's surface corresponds to a temperature of 278 kelvins or about 5 degrees Celsius in our bare bones model. This result is significantly colder than actual Earth, but our model is clearly missing some important pieces. Something we cannot determine, or like you could say is anonymous, but we'll try to discover and figure that out more later in this exercise. Continue. So far, we've ignored Earth's atmosphere, but the atmosphere is critical to Earth's temperature because it interferes with Earth's energy flows, that how much sunlight it absorbs and how much radiation it emits. So these two arrows in opposite directions coming in and out of the energy balance that matters. Wait, if we added an atmosphere to a model that only transmits half the energy going through it both directions, blocks the rest, how do you think will affect the Earth equilibrium temperature? So need to reduce this energy, so I think like this. Oh, you obviously see like this energy in is reflected, this is also reflected back at the same time. So like if we say halfway, then equally reflected back to space or back to the Earth's surface in opposite directions. So will it warm up, stay the same temperature, or cool down? Block the rest. I think it would cool down. Oh, actually this wouldn't change the Earth's temperature at all. So here's why. Equilibrium temperature corresponds to a balance between emitted and absorbed radiation. Adjusting these flows by the same amount, like half AI or half Ca doesn't actually change balance, so overall it doesn't change the equilibrium temperature. Simply no effect. Temperature remains unchanged, like kind of being constant as a result. So continue. There is a key part missing to our model so far. Earth mostly emits energy as infrared radiation, whereas sunlight includes visible light. Oh yes, like sunlight is in, infrared radiation is out, but something like key part which we cannot determine at the moment yet, but hopefully we'll discover that later on. Continue. This means the atmosphere can affect Earth's energy flows differently. We can characterize the atmosphere with two properties, its solar and infrared transmittance. Transmittance is proportion of energy that atmosphere allows through. If we reduce infrared, emitting back to space is less, but more will be trapped back into the Earth's surface. If it's greater, more emitted. Almost at the same time, solar reflect into space if transmittance is too low or just directly to the Earth's surface, no reflection if transmittance is too high. We just adjust them to analyze what would happen in each circumstance. Wait, how might an asymmetric atmosphere, one with different solar infrared transmittances, balance towards a warmer Earth? Let's say more sunlight than infrared or less sunlight than infrared. Warmer Earth, so less sunlight than infrared. Oh, actually, that will lead to a colder Earth. If the atmosphere transmits more sunlight than infrared radiation, then the energy flow out of Earth is reduced relative to the energy flow in. So Earth's equilibrium temperature would be higher under this atmosphere compared to a symmetric atmosphere. Overall, this is naturally a simplification. The diagram suggests that any redirected sunlight is being reflected back towards space by the atmosphere, and any redirected infrared radiation is being reflected back towards the ground. But the reality is more complicated. Okay, hopefully we should observe this later on. So continue. Now, considering solar transmittance, which variable S, and infrared transmittance variable T, the energy absorbed by Earth is now SAI, and energy emitted becomes TCA power 4. Change our balance to the following. Now, isolate the TEQ4 term again. So this time should be, wait, SI divided by TC. Let's check it. Yup, that's correct. Why for reasoning? Similar to before, both flows depend on the Earth's area A. Dividing this common factor out gives S times I equals TCEQ4 and so on. Isolate TQ4 term we divide by T and C, which yields TQ equals SI divided by TC. Continue. Taking the fourth root of both sides yields our new expression for TEQ. TEQ equals the SI divided by TC to the square root of 4. Since S and T can be different, our model can now lead to equilibrium temperatures for Earth that don't only depend on I. Let's see if it can do a better job matching the Earth's actual surface temperature. Find atmospheric parameters that lead to an equilibrium temperature between 12 degrees to 16 degrees Celsius. Wait, I need to scroll down like this. 12 to 16. Equilibrium temperature. What does that mean? If I increase this is less. Parameters. This is 12. This is 16. So T is lower, S is higher. So these values 0.688 sunlight and 0.55 infrared. Let's check. Oh, It should be lower than this. Oh yes, this is not correct. Between, so like, let's say this 15 and 14, shall we? Oh yes, that's correct. Let's see why for reasoning. There are many combinations of parameters that lead to equilibrium temperature, which is near 14 degrees Celsius. If the current equilibrium temperature is above 14 degrees Celsius, lower solar transmittance or increased infrared transmittance. S is lower and R is higher. If the current equilibrium temperature is below 14 degrees, increased solar transmittance or lower infrared transmittance. One example that leads to this value is such that S equals 0.57 and T equals zero point 0.5, approximately 13.8 degrees Celsius that compromise Earth temperature. Wait, you can see mine is a bit different, like close to 40 degrees Celsius is also acceptable. Doesn't matter which range the values might be accepted. Anyway, click continue to proceed the next screen. We've built a simple model that can reproduce Earth's measured average temperature. Let's see how it can help us understand global warming. Some sunlight does get reflected by the atmosphere itself, but much of it is reflected by the Earth's surface. Climate scientists typically characterize the total proportion of sunlight reflected back to space in a parameter called albedo. Our solar transmittance is basically I no 1 minus albedo, since any reflected sunlight won't be absorbed, regardless of what is actually doing the reflecting. In fact, since we don't need an atmosphere to reflect sunlight, a more accurate estimate of the average intensity absorbed by Earth is around I equals to 240 watts per meter squared. This corresponds to an equilibrium temperature of about 255 Kelvin or minus 18 degrees Celsius, atmosphere-free Earth, which is close to actual average temperature of the moon. But it's freezing, right? Continue. Our diagram shows infrared radiation being reflected back to Earth's surface, when in reality, atmosphere mostly absorbs this radiation. In this case, it isn't too important to distinguish between reflecting and absorbing the radiation because in both cases, the radiation will not escape to space. Anyway, click continue to see what's next. While this model of our atmosphere is a simplification, it will still allow us to make reasonably accurate predictions about Earth's equilibrium temperature as atmospheric properties change. Our model is a massive simplification. Wait, need to scroll down. Massive simplification of all the physics that affect Earth's surface temperature, but if we compress reality into these parameters, then a solar transmittance of S equals 0.7 and an infrared transmittance of T equals 0.615 roughly correspond to the pre-industrial atmosphere. This approximate temperature of 268.9 Kelvin. Like this. So if we just like lower T is also small, lower S, then sunlight was small. So T and S were contrasting. So just brief observation here. Continue. Now these parameters change as we add chemicals to the atmosphere. The one most relevant for climate change is carbon dioxide, also known as CO2. Wait, need to scroll down. Wait for a moment. Here. Pre-industrial CO2 levels were around 280 parts per million, meaning that for every million molecules in the atmosphere, 280 were CO2 molecules. But tremendously increasing, and we have now reached almost 420 parts per million now as the present day in the decades of 2020s. Incredibly large compared to the pre-industrial times, like more than 2 centuries ago in the past. Right, just the comparison between year and CO2 concentration in the atmosphere. Continue. Yes, CO2 mainly comes from burning fossil fuels. The smoke that gets released is a mix of chemicals, some which you can see, but CO2 is invisible. Do you think adding CO2 will affect how much sunlight the atmosphere lets through? Hmm. Yes or no? I assume it must be yes. Oh, actually, CO2 is transparent to the visible light that makes up a significant portion of sunlight, but CO2 does interfere with infrared radiation. Adding 100 parts per million of CO2 to the atmosphere decreases infrared transmittance by about 0.004. Wait. But leads to only a negligible decrease in solar transmittance. This interactive shows the effect of reduced infrared transmittance as more CO2 is added to the atmosphere. So if I adjust this atmospheric carbon left very low and increase it, yes, parts per million of CO2 also increase proportionally, and average temperature increase also slightly increase at the same time. But infrared radiation is somehow affected and reduced. So this maximum value is 600 parts per million plus 1.3 degrees Celsius temperature increase. Like too much CO2 into atmosphere is not a very good idea, only caused by like human activities. So back to this minimum, atmospheric carbon is the best possible option. Continue for the next screen. Current atmospheric carbon levels are about 420 parts per million, 140 higher than pre-industrial levels. Does this fact of CO2 infrared transmitters alone explain the 1 degrees increase in average global temperature? Oh, this CO2 effect? Probably not, no. Yeah, actually no. So why is that? Wait. Setting CO2 concentration to 400 parts per million leads to infrared transmittance only about 0.61. Only about half of the observed 1 degree temperature increase, so CO2's direct effect on infrared transmittance doesn't fully explain the climate change we're witnessing. No, there's no direct relationship why this cause and effect are both occurring at the same time. Insufficient evidence, to be honest. So continue here. If the direct effect of carbon dioxide was all we had to worry about, we'd be in much better shape. Unfortunately, Earth isn't a static system. When temperature changes due to increased CO2, other parameters change too. Consider another part of the atmosphere, water vapor. Yes, water vapor is similar to CO2 in that it blocks infrared radiation but is basically invisible to sunlight. Similarly, not visible by the naked eye, as I described previously. Continue. Now, if temperature increases, how do you think that affects the amount of water vapor in the atmosphere? I say vapor might chance to increase, but probably I'll choose this. Doesn't affect the amount of water vapor. Oh, not quite. Higher temperatures lead to more evaporation, more water vapor in the air. This is why summer is generally more humid than winter. As Earth's average temperature rises, amount of water vapor in the atmosphere increases. So, how does the presence of water change the overall effect on CO2 has on Earth's average temperature? CO2, is it stronger overall effect, weaker overall effect, or doesn't change? Yes, that should be stronger overall effect. Let's check. Yup, that is correct. So why for reasoning? Yes, higher levels of CO2 raise the temperature, which lead to more water vapor in the atmosphere. Water vapor also interferes with infrared radiation, so the total amount blocked is greater than what results from the CO2 itself. Overall, CO2 generally has a stronger effect than we initially consider. So something you have to keep in mind when we make these theoretical comparisons and assumptions. Continue to the next screen. Water vapor is like a CO2 multiplier. More atmospheric CO2 increase raises the temperature, which leads to more water vapor, which further raises the temperature. This is called a feedback loop. since the output of increased temperature feeds back into the input, called atmospheric makeup, further influencing the output. Input-output cycle both are affected like as a result of feedback loop. So showing these arrows back and forth between relationship between temperature and CO2 molecules effect. Right. So continue to the next screen. Yes. Atmospheric water vapor is just one feedback loop that influences climate change. Increased global temperatures can trigger other feedback loops as well. So here they are. Polar ice reflects sunlight. When it melts, more sunlight is absorbed. And second, greenhouse gases with a similar effect as CO2 are also trapped in permafrost, soil in polar regions that typically stays frozen year-round. If regions of permafrost melt, they release these gases into the atmosphere. Similar relationship in this diagram, back and forth cycle, how these glaciers, polar ice will be affected depending on the CO2 concentration levels. Continue. Now, given these feedback loops, adding 100 parts per million of atmospheric carbon effectively leads to a greater than 0.004 decrease in infrared transmittance. Find the effective transmittance reduction that will lead to our ozone temperature rise of around 1 degree Celsius. So here, transmittant reduction plus 1 degree Celsius. These S and R values, they will somehow change, I think. We need to increase to plus 1 degrees. So, wait. Here we go. Plus 1 degree Celsius, 0.006 per 100. Let's check. That's correct. Why for reasoning? I need to scroll down. It takes an infrared transmittance reduction of around 0.006 per 100 parts per million of CO2 in order to explain the observed 1 degree temperature rise at our current levels of atmospheric carbon. For reasons we'll see shortly, this is actually a low estimate, and also infrared transmittance dropped by about 0.01 per 100 parts per million of CO2 added to the atmosphere. So just as that, I just adjusted this temperature, and also these all variables might change, but we'll observe these later on. Continue. Roughly speaking, adding 100 parts per million of CO2 to the atmosphere reduces atmospheric infrared transmittance by 0.01, with 0.004 coming directly from the CO2. Those increased level of atmospheric water vapor and 0.002 coming from other feedback effects. Wait, like this. This plus 100 is equal 0.01. Because of reduced infrared transmittance, this water vapor, CO2, other effects, they are like rough estimations how much concentration will be affected by when you generally consider these two global problems. Our model predicts lower reductions around that 0.106 per 100 parts per million of CO2 to explain 1 degree Celsius of warming. We'll see what's causing this discrepancy shortly. Continue to the next screen. Without feedback effects, the Earth would still be significantly cooler than it is now, and we'd have more time to tackle climate change. Given the reality we face, let's see what it would take for us to keep climate change in check. Something we still have to discover later when we reach the closing stages of this chapter. Continue. Yes, our model can predict the equilibrium temperature of Earth given the amount of carbon dioxide in the atmosphere. This means we can use it to determine how much more CO2 we can emit while staying within certain temperature targets, called a carbon budget, so to speak. If humanity can stick to this budget, we can avoid climate faster. Look at this. Increasing CO2 budget, like avoid climate disaster, but wait, would you believe it? This diagram's absolutely ridiculous. What do you think of this? Give your opinion in the comments as well. Continue. I need to scroll down a bit. Wait, here. In 2015, nations of the world agreed to a climate pact known as the Paris Agreement. Intended goal was to limit global warming to just 1.5 degrees Celsius. Again now, according to a model, what level of atmospheric carbon does a 1.5 degrees Celsius temperature rise corresponds to? So if I scroll this to here, around 426 parts per million of CO2. Let's check. That's correct. Why for reasoning? Yes, based on our model, atmospheric carbon concentration around 420 parts per million corresponds to 1.5 degree temperature rise. Again, simple adjustment and observation that I show up to you. Continue. Now, our model tells us roughly 420 parts per million corresponds to 1.5 degrees temperature rise. But already the similar amount CO2 present in the atmosphere, but the current temperature rise is only around 1 degree Celsius. So 2022, like temperature rise only about, so like line of best fit actually goes out of this range. Line of best fit, like kind of a bit of an anomaly. Oh, why doesn't the current temperature rise match our model's prediction? Let's see. We don't understand all feedback effects at play. It takes time for Earth to heat up. Climate change is a hoax. Let's click one of those assumptions. Which one should I pick? Yes, takes time for Earth to heat up in a constant amount of time. Yep, that's right. When energy flows are out of balance, the temperature changes, but this change isn't instantaneous. Right now, the energy flow into Earth due to sunlight is greater than energy flow out due to infrared radiation, so the Earth is accumulating energy and heating up. Same balance reverse process. Continue to the next screen. Right. If we limited atmospheric CO2 to 420 parts per million, Earth's temperature would continue to rise, eventually setting at an equilibrium temperature about 1.5 degrees Celsius above the pre-industrial average. So directly looking at this year versus carbon, mass of carbon in the atmosphere relationship. Wait. This is why our model underestimated the infrared transmittance reduction corresponding to the current 1 degree Celsius of warming. Earth's surface temperature hasn't caught up with the amount of carbon dioxide we've emitted. Continue to see what's next. We're well on our way past 1.5 degrees of warming, but the ultimate goal of Paris Agreement is to limit global warming to well below 2 degrees Celsius. While a rise of exactly 2 degrees isn't well below that 2 degrees, it gives us a bigger carbon budget. Now, according to our model, what level of atmospheric carbon does a 2 degrees temperature rise corresponds to? Need to adjust this to, wait, around this point. Let's check. Correct. So why for reasoning? Based on our model, an atmospheric carbon concentration of around 470 parts per million corresponds to 2 degrees temperature rise. Simple explanation and observation here. So just as basic. Continue. Our model tells us we can reach about 470 parts per million CO2 while still limiting global temperature rise to 2 degrees. Current level of atmospheric carbon around 420 parts per million, increasing about 2.5 parts per million per year. So at this rate, how long can we keep emitting carbon before we reach a 2 degrees increase in global temperature? Around 2020, 2.5 parts per million per year. So 50 divided by 2.5 would be 25 years. Done. Let's check. Oh, run out of carbon budget before then. Oh yeah, 1.5 degrees. 1.5. is 2, 0.5 degree. Start over, like, let's assume 50 years. Done. So too large value isn't correct. Let's say like 10 years, isn't it? Let's say around 15, another estimate. It should be 20. Yup, 20 years is the best approximation answer. Oh yes, I had to go several attempts here. Sorry for my apology. Let's click wife reasoning. Oh yes. Budget for 2 degrees, 470, 420, so difference is 50 parts per million. Oh yes. Divide by 2.5 parts per million per year, so exactly 20 years left before we reach this budget. So too many years, then already run out of budget, so out of estimation. Sorry for my miscalculation. It should be 20 years, best approximation value. Alright, let's click continue. Completely decarbonizing world's infrastructure in 20 years is an incredibly tall order, especially given that global carbon emissions are still increasing most years, not decreasing. So this value increasing somehow but might decrease at some point if the target is successful or kind of showing different anomaly. Now, and don't get too excited about the recent dip. This is more likely a pandemic-induced blip, not the start of a rapid downward trend. Anyway, let's expand our carbon budget a bit further. A few more explanations to go before this chapter shuts off. Continue. A temperature rise of 3 degrees will lead much more hostile planet than 2 degrees, enormous suffering and destruction, but it won't lead to apocalyptic extinction of humanity. What atmospheric carbon level can we afford to reach if the goal is to stop at 3 degrees of warming? Okay. 3 degrees increase, yes. So if we continue scrolling this from left to right, around here, maybe? Let's check. Yep, correct. Why reasoning? Based on our model, an atmospheric carbon concentration of around 560 parts per million exactly corresponds to 3 degrees of temperature rise. That's massive amount that you will previously observe in 1 degree, 2 degrees increase, and now 3 degrees has more big influence on how Earth might change to adapt itself. Click continue. Yes, if we only need to limit 3 degrees of warming, we have a much more generous 560 parts per million carbon budget, significantly higher than our current population of 420. Now, we need to find how long we could keep emitting at the current rate of 2.5 parts per million per year before hitting exactly 560 parts per million. Again, need to find this answer mathematically. 140 divided by 2.5 is 140 divided by 2.5 is, yes, 56 years. Done. Time to check it. That's correct. Wife reasoning. Yes, we have difference of 140 parts per million left in current budget. Increase at 2.5 million per year. Again, the same rate. Let's give a divide 140 divided by 2.5, 56 more years. Okay, now that's the correct assumption after all. I now solve it mathematically correct. So continue to the next one. Wow, we're almost there to conclusion. Anyway, let's try to finish this off. It is much more realistic that we could transform global infrastructure in 56 years than in 20 years. Many nations have set goals of achieving net zero carbon emissions by 2050, which should keep us within 3 degrees carbon budget. It's feasible that we'll be able to limit warming to 3 degrees if we follow the path we already on. Look, These creatures approximately like 2030, 2045, 2050, 2060. Achieved. Wow, lots of different opinions, but like kind of arguments being too much debate on these characters, but we will have to consider that. Never mind. Continue. Right. Last but not least, this is the final statement. 3 degrees still corresponds to untold suffering, and reality is more complicated than our twin model, so we should aim for as small a carbon budget as possible. We need to continue the work that is slowly tilting our global infrastructure towards sustainability. The more we can pick up the pace, the better off we'll be. Look, kind of more we're generally approaching like the sustainable work, wind energy, solar energy, electric trains, more tree plantations to improve our environmentally friendly, lots of resources. Like we just have to keep praying for lots of preparing this infrastructure in terms of science and effects of global warming, how it might impact in the future. Right. Thankfully, this exercise has come to an end, so I'll click finish to sum up. Wait. Lesson complete. That was an extremely long, enduring lesson that I had to like record this for like up to half an hour in duration. Anyway, I've gained 255 XP this time around. Continue. Boom. Wow. Another successful extended streak. My streak rating 10 out of 10, which means 10 days in a row after this long climate change exercise lesson that I've had on Sunday here. Continue. Learn faster with personalized practice only on Premiere. No, it's not necessary after all. Remind me later. Wait, hold on. Alright, there we have it. Kurzgesagt, beyond a nutshell, this climate change long exercise has successfully completed by Rooney Lin in today's educational video so far. So yes, that's it for this educational video that I've created and presented to all of you. Thank you very much for watching this, and if you do so, don't forget to add a like as always and subscribe to my YouTube channel to check out for other related educational videos that I demonstrate to you. But I will not be stopping my progress from here. I'll still continue creating similar educational videos in the future. Just stay tuned and check out my YouTube channel for the following description. That's it guys, everyone. Take care guys. I'll see you in the next video. Cheers. Bye.